Welcome back, Kevin. Sarah, you made it.
Yeah.
Sorry, I don't know what was going on. Now I just changed the permissions so anybody can join.
Okay.
So if we give it like 2 minutes, I think people will be able to sign in.
Yeah. I think the problem was some of us aren't on Google Plus, and so it doesn't let you have access to the event even though you're added. It's weird.
Interesting. That makes sense.
Yeah.
I should have actually posted about that yesterday. Yesterday night. If you make a Google Plus ahead of time, it works a lot better.
Yeah.
All right. Well, so basically, once everybody's in, I'm just worksheet questions or Math Excel questions. That's the basic idea. So. Got this cool little thing where I can ink on my iPad and then it goes onto my screen, which is kind of cool. Yeah, let's see who we've got in here. Oh, still only 3 people. Wait, oh, Angie's back.
Hello.
Hi, Angie. Hi, Viva.
Hello.
All right, I think that's enough people to start. If Google Plus accounts are still giving folks a hard time, I don't know if they're going to fix that anytime soon. So we had just finished up a Math Excel problem. I think we should maybe look at anything from the worksheet that came up. So you guys can just kind of throw out worksheet numbers, worksheet problem numbers, and I'll do those. Charant is still kicked out of the event, which is weird. Oh, he doesn't realize it's a new Hangout. Oh well, he will figure it out. All right, I guess what I'll do then, since no one's asking, I'm just going to pick one that I think is really good to know how to do. Where is it? There we go. Like 5 and 6, I think traditionally students have found those kind of confusing on the chapter test, problems like that. So I think it's worth showing the steps that go into a problem 5. So 5, they want you to come up with a Maclaurin series expansion for f of x equals sine of x over x. And what you know is that sine of x has a nice little series that you've already memorized, right? So sine of x could be rewritten as its series expansion, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and, you know, plus dot, 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 just keeps on going forever. And then that entire infinite series is being divided by x. So you're basically just kind of following the order of operations here. You're doing x divided by x. You're doing x cubed over 3 factorial divided by x. You're doing x to the 5th over 5 factorial divided by x, you know, and so on and so forth. In fact, you could take the general term that nth term and also divide that by x, and you can figure out the sigma notation. So x divided by x is just 1. And then x cubed over 3 factorial divided by x is minus x squared over 3 factorial. X to the 5th over 5 factorial divided by x, we have plus x to the 4th over 5 factorial, and so on and so forth. So plus dot dot dot. And then what you could see in the answer key, what I did was I just did this whole thing in sigma notation. So I just went straight to the degree n term with the summation notation and then divided that whole thing by x. I followed the same process. Every term is being divided by x, so x to the 2n plus 1 divided by x to the first is x to the 2n, and that's where that answer comes from for 5.
Wait, so if we're direct substituting for like a series, do we have to write down like direct substitution by this series or whatever, or can we just like do what the answer key says?
No, I think the answer key is fine. The only reason I'd ever write down like direct substitution or something like that is if I thought it was confusing or ambiguous. So if
Okay.
you're doing something that you thought like, oh, I'm not sure if the grader is going to understand what I just did, then maybe I'd mention that it's direct substitution. But no, the answer key is pretty much what you'd have to do.
Okay, thank you.
Yeah.
Oh,
Go ahead. What's up?
if we do direct substitution, should we put the original series first and then the substituted one, or can we go directly to the substituted one?
On the AP test, I maybe would show the original and then show the substitution. On this test, I wouldn't worry about that.
Okay.
I think you'll be fine. Let's see here. Oh, you know what? Which other one I like? So 5 is useful. 6 I think is even better, because on number 6 there's direct substitution and there's order of operations in it. So let me show you how you would go about doing number 6. For this one, you have f of x equals x over 1 plus x squared. You're better off thinking of that as x times the quantity 1 over 1 plus x squared. So 1 over 1 plus x squared, that's really similar to the Taylor series you guys know for 1 over 1 plus x. We're just going to do a direct substitution where x gets replaced with x squared. And then in contrast, this x on the outside is an order of operations thing where it's going to be distributed to the series that's inside. So my second step here, I would say equals x and then a big old set of parentheses. And you guys know what 1 over 1 plus x is, hopefully, right? 1 minus x squared plus x squared squared minus x squared to the third, and so on and so forth, plus dot dot dot. And then the only step that's left is to distribute this x to all of these terms. And that's where you end up with this final answer that's on the answer key that says like x minus x cubed plus x to the 5th minus x to the 7th, because like for this x to the 7th one, that's just x squared cubed times x to the 1st. And then don't forget your plus dot dot dot. Oh, you couldn't see anything I just did. Didn't realize that. There it is. X minus x cubed plus x to the 5th minus x to the 7th plus dot dot dot. And then if you compare that to what's in my answer key, I did the same thing there. I just also showed the sigma notation, which is a much more condensed, compact way of writing it. So. All right. So anything else you guys would like me to go over? Worksheet, Math, Excel, general questions.
Can we go over number 9?
Yeah. Oh, hey Melinda, did you just sign in right now?
I caught most of the last example.
Okay. Was it the Google Plus account? Was that the issue?
I don't know. I just found something in my email that said FHS Math was inviting me to join his Hangout, and that's how I got in.
Oh, good. Okay. Yeah, I tried to send you guys all invites so that you had a direct link to it, but okay, let's see here. Someone asked about 9. Here's 8. We'll go back to 8 in a second. And here's 9. Yeah, so for number 9, that one, so there's two ways of going about number 9. The first way you could do number 9 is you could say, hey, that's not centered the same place that the Taylor series on my worksheet is centered, right? Like you have those Maclaurin series that are centered at x equals 0, and you could use direct substitution and all that sort of stuff when you're still centered at x equals 0 and you haven't shifted the function. And so you might be like, it doesn't look like the sheet. So what I'm going to do is I'm going to use that formula that we memorized. I'll show you the formula. And you could derive this formula term by term. That's one option. It's not my preferred option, but I'm going to show you how that would work. Because it's kind of the foolproof way of doing it. Like this will always work no matter what the problem is. So you use, uh-oh. Let's see, why is this not showing up? Oh, good, it is working now, okay. So anyway, you use this formula. Okay, I just wrote another sigma symbol, it's not showing up. Oh, just scroll up. That's what it is. Okay, anyway, so you use the formula, the sum from k equals 0 to infinity of the kth derivative evaluated at the center of the series A over k factorial times x minus a to the k. That formula will always work for deriving any Taylor series you're looking. As long as you can keep taking derivatives of the function, you know that formula is going to let you derive what you're looking for. And then now we know that a is supposed to equal 1 because they told us that the series should be centered at 1, and your f of x is the natural log of x. So those were all of your given bits of information. So if you wanted to, you could go ahead and say f of x is natural log, f prime of x is 1 over x, f double prime of x is negative 1 over x squared. And you keep on going on like that and taking lots and lots of derivatives. Then you could plug in to each of these with the center. So you could do f of 1 is equal to 0, and f prime at 1 is 1, and then f double prime at 1 is negative 1. And it just keeps on kind of going like that. And then you plug into the formula, and you'll get this. You'll get that degree 4 Taylor polynomial. It'll work. We just have to go all the way up to a fourth derivative, which is not necessarily the most fun thing in the world. However, the thing that once you're getting kind of advanced with this, what you're going to notice is the series that you have memorized is natural log of 1 plus x, and it's centered at an a value of 0. And then the series that they're looking for, the one that they want you to figure out, is natural log of just regular x, and it's centered at a equals 1. Well, if you want, you could kind of think of natural log of x as natural log of 1 minus 1 plus x, right? Because 1 minus 1 is 0. Or you could think of that as natural log of 1 plus x minus 1. It's the same thing, right? I've just reordered the terms, which you could see that I'm shifting or recentering this series at 1, and the center that they're looking for is also a equals 1. And so it would be perfectly valid. I know this was kind of a long story to get to the point here. But my point is you actually can use direct substitution here. So it would be okay to pull up that list of all the Taylor series that you have memorized. And in that list, I mean, you already know it. It's natural log of 1 plus x. It's one of the ones that you've already been quizzed on. But it would be perfectly fine to grab this series for natural log of 1 plus x, and just do a direct substitution here. And so that's how you can tell. Look at how this degree 4 Taylor polynomial looks exactly like the first 4 terms of natural log of 1 plus x, except for x is being replaced with negative 1. Yeah. So basically replacing x with x minus 1 because you're recentering at x equals positive 1. So that's how you can get the first 4 terms really quickly. And then what else are they asking for here? Find the Taylor series in summation notation, sure. So this is just rewriting the Taylor series with a sigma rather than just listing out all the terms. But you can see how it goes. The series alternates, and it starts positive. That's where the negative 1 to the n minus 1 came from. And then the over n, you can see these denominators, they're over 1, then over 2, then over 3, then over 4, so on and so forth. And then these powers are also counting up. So that's where that sigma notation comes from. And then for part C, they're just asking you to integrate term by term. So they're just wondering, like, can you take a Taylor series that you have derived, and can you go term by term and take the integral of each of those terms, and can you manage to do that with the general term as well? I can kind of show you how that goes. It's nothing too crazy. By the way, guys, since we got started late, I'll stay on here till 2 o'clock instead of just 1:50, just in case there's more questions that I didn't get to or anything. Okay. Anyway, so if you look up at the top of my screen where I've got a little scratch pad, it would be okay to take the original series x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed, and then I'm going to go plus dot 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 plus, then I'm going to go negative 1 to the n minus 1 over n times x minus 1 to the n, and then plus dot dot dot. That's the original infinite series. To integrate it term by term, you can just literally, like each term, just integrate each one from 0 to x. So this would be x minus 1 squared over 2. Then this next one minus, I have this 1/2, and then I also have to divide by the new power I'm about to get. So minus 1 over 2 times 3 times x minus 1 cubed. I mean, you probably get the idea here. Plus 1/3 times the 4 that I'm going to get with my new power there. And then I'm going to go plus dot dot dot. And then probably the most important one is this general term. Oh my gosh, I didn't realize you can't see that. I'm looking at my iPad, not my computer screen. So, okay. Anyway, to do this last one, the negative 1 to the n minus 1 is not changing. There's no x's in that, right? So when you're integrating with respect to x or with respect to t or whatever, negative 1 to the n minus 1 is not a variable. It's constant relative to that integral. And so just you could carry down the negative 1 to the n minus 1. Same thing with the over n. That is also not changing. And then I have x minus 1 to the n plus 1. But if I have n plus 1 as my new power, I need to divide by n plus 1 as well. And that's your formula. And it should match up pretty nicely with what we have right here. And then the only other thing you should notice, this general term starts to work at n equals 1. So it's not a bad idea to mark that in your answer. N equals 0 will mess that thing up, so because it's not the first term anymore. So this starts at n equals 1. Yeah, that was a great question. Number 8's a really good one. Anybody else?
Could you do number 7?
Yeah. Oh yeah, so 7. This is a good one because this one we don't have any flexibility with substitution. Like there's no tricks I can use like I was showing you on the previous one. F of x equals cosine of x wants to be centered at x equals 0, but we're recentering it at pi over 4, and so there's no consistency there between the function and the center, meaning like our only option here is to derive this term by term. And you could pretty much guarantee on the test you're going to see something like that where you have to, let's see, let me clear this out. And then let's bring up the worksheets. They're side by side. Perfect. Yeah, so anyway, on the test something like this will happen where you're going to have no option but to use the formula that is general to all Taylor series. The sum from k equals 0 to infinity of the kth derivative at a. In this case, a is pi over 4, so I'm just going to put pi over 4 in there straight away, over k factorial times x minus a, but in this case, a, the center, is pi over 4, so x minus pi over 4 to the k. So that's the formula that we have to work with. And in order to make this all work, I need to know, hey, what's the 0th derivative of f? Well, the 0th derivative is just a function. F of x equals cosine of x. You need the first derivative, negative sine of x. Then you need the second derivative. And let's see, how many terms did they want? Did they say the first 3 terms? Let me see what's... They want maybe the degree 3 Taylor polynomial? Yeah, okay. So f double prime at x is negative cosine. Now, when they say the first 3 non-zero terms, I don't know how many derivatives I'm going to have to take until I have 3 non-zero terms. So sometimes you end up taking one more derivative than you need. So you can see in my handwritten work, I've gone up to the 3rd derivative. In the answer key, I only went up to the 2nd derivative because, when you're writing an answer key, you erase any extra stuff you don't need. But in this case, it's not a bad idea to go up to this 3rd derivative. Now we're going to evaluate all of these at pi over 4. So f of pi over 4 is root 2 over 2. You start to have to know your unit circle to get that. And then you would just keep on going, right? Like f double prime, or sorry, f single prime at pi over 4 is negative sine of pi over 4, so negative root 2 over 2. Luckily, the only thing, the root 2 over 2's keep sticking around, and the only thing that's kind of changing are the signs. So you have another negative root 2 over 2. If you did go up to the 3rd derivative, you'd be back to a positive root 2 over 2. Once you have these coefficients, you're done, right? Like this is the hard part of the problem, is finding these coefficients. Because the rest of it, you're plugging into a formula. You're plugging into like a recipe. And that recipe is that sigma notation I was showing you before. So you can see I've got my coefficient of root 2 over 2. Then f prime at pi over 4 was negative root 2 over 2. Divided by 1 factorial, but you don't need to do that. And then times x minus pi over 4 to the first. And this second derivative was another negative root 2 over 2, divided by 2 factorial. And then times x minus pi over 4 squared. So that's where this thing came from. Same thing happens in number 8, where your only choice is to take a bunch of derivatives, find a bunch of coefficients, and kind of plug those in. Any questions on that? Anybody?
Could you go over number 7 from the 10.3 Math Excel?
Sure.
Thank you.
Yeah, no worries. Oh, is it this one? E to the x is this degree 2, yeah, okay.
Yeah.
So one thing that might help you on that one is I posted a YouTube video to Schoology. Let me show it to you. That for all these people that weren't able to sign in. Let's see how many people are complaining about that. I just don't know if there's any way I can fix it. I think Taranth got the invite and you just didn't know how to click it. There's totally a link there. All right, anyway, I posted a YouTube video today that walks you through how to do that, that exact problem. Hold on, let me mute this. Oh God, what just happened? Taylor Swift, that's crazy.
All right, guys, thank you.
There. Oh, Taylor's theorem. Taylor Swift biography. It thinks they're related. Crazy. Anyway, on this YouTube video, it basically does that homework problem for you. So if you search section 10.3 Taylor's theorem day 1 or FHS math, which is my username, it'll walk you through this problem. I'm going to do it anyway, so you can still see it. But this will explain line by line why you're doing each step that you're doing, which is probably going to be more helpful than what I'm going to do right now, which is just do the problem. So.
Thank you.
Yep, no worries. So anyway, they want you to find the maximum error when you're using the degree 2 Taylor polynomial to approximate e to the x. So they're basically saying, hey, e to the x is pretty well approximated by its degree 2 Taylor polynomial. The problem is we don't know exactly how well e to the x is approximated by its degree 2 Taylor polynomial on. And so what we want to do is have an error estimate that gives us an idea of, like, hey, is P2 of x doing a good job? Is it not doing a very good job? Like, how close are we actually approximating e to the x when x is between -7/10 and +7/10? That was given to us in the problem. They're just saying, hey, we're only going to be working with values of x that are this, within 7/10 of x equals 0, and how well are we doing? So if we have P2 of x, our error bound is going to be the next term in the series. So what you would do is you'd take your function and take its n plus first derivative, and I guess n plus first would be the degree 3 derivative. Evaluate it, in this case, at a value c that we have to determine in a second. Oh, you can't see anything I'm writing. Let me move this. There. So we need the third derivative of f at c divided by 3 factorial times x minus 0 to the third. Basically, oh, that's a really ugly 3. Let me fix it. That's going to bother me if I don't. Yeah, like that. So this is Taylor's theorem. It's the Lagrange error bound. And what the Lagrange error bound says is you could figure out how much error you have in your approximation by taking the next term in the series. And basically everything in here is going to be the next term except for there's this weird c value. And what the c value is it's whatever value we need to take on our interval that makes this thing as big as possible. So I want to maximize the third derivative at c on this interval. Luckily, finding the third derivative of e to the x is like the easiest thing ever. F triple prime of x is just e to the x. And also maximizing e to the x on a closed interval is also very easy because you know that e to the x is a monotonically increasing function. It's always getting bigger and bigger and bigger. And so to make e to the x as big as possible, our c value should just be the biggest value on our interval, which is 7/10. So long story short here, let me show you our error bound. Let me move this out of the way a little bit. What I want is I want e to the 7/10, the third derivative evaluated at 7/10, over 3 factorial, times, and then our x value also needs to be as big as possible on our interval, and that's also 7/10. And when you run that through a calculator, you're going to get some decimal. That's an upper bound for the amount of error that we have on our interval using a degree 2 Taylor polynomial, where x value is restricted to negative 7/10 up to positive 7/10. And that decimal, when you plug it in, should work. And I don't know what they're talking about, this M thing. They have some weird notation with the letter M, but I'm assuming it's probably like the interval size. I'm not sure. I don't use that in my class, but you guys can pipe in. But it's probably M equals 7/10 or something. But you're going to fill in the blanks here with that decimal. Okay, cool. I probably have time for one more. If there's one last one you guys want to do before 2 o'clock. Anybody? All right, if you guys are good, I think I'm going to sign out then. Have a great day. Enjoy the rest of your snow day. Check out that YouTube video, and I think you should be in pretty good shape then.
Thank you.
Thank you, Mr. Griffin.
Thank you.
No worries.